Well, this injector is a LOX hydrogen, or liquid oxygen hydrogen injector, built by the direct metal laser sintering process, or DMLS process. Well, the main thing that we'll be monitoring here will be the combustion chamber pressure, the fuel temperatures for both the liquid oxygen and the hydrogen, and other pressures throughout the system, such as the manifold pressures in the injectors. Well, it's an important objective for the Space Launch System because we haven't tested something this scale before at 20,000 pound thrust level. What we want to do is take this test data and compare it to test data for a conventional machined injector and see what the differences are in performance and what kind of flow differences there are. Traditionally, the engine has been one of the longest lead items for the vehicle, and so this process then allows the potential to be able to produce parts much faster and less expensive.
We want to build rocket parts and test them with additive manufacturing because it's a new class of fabrication technology that really hasn't been tested out, but the benefits are great in that you can build structures not only that you couldn't build before, but you can build existing structures a lot faster and a lot cheaper. There's a lot of qualification effort that goes into even just testing a new variation on a material. So since this is a completely new manufacturing process, we've got to put the techniques down from cradle to grave, from the design to build to test to qualify to certify for this whole new fabrication technology. So Marshall's goal with all the work we're doing in 3D printing or additive manufacturing of rocket engine parts is to develop a collective set of guidelines or a handbook so that when we go out to American manufacturers or our contractors and say, we want a 3D printed rocket engine part, they've got guidelines to follow so that they know they're going to make us a good part. It's not to qualify a part, it's to qualify the process.
One of the advantages that the additive manufacturing allows is that it allows designers to incorporate complex internal flow geometry into the injectors that they would not be able to do with conventional machining processes. Conventionally, a part of this size, an injector of this size, would have hundreds of parts, and so the additive manufacturing allows us to do all of that in really 2 parts. And so we want to see, is there any difference in injector performance by consolidating all these parts? Well, this is important for all of liquid propulsion systems because we can determine what parts are going to be feasible to use the additive manufacturing process on a real engine.